This conference will now be recorded.
All right, so today we're going to get together and talk about the stochastic empirical loading and dilution model, SELDM. And this first little presentation is just going to talk about like how we're going to run this course. For the people who have heard my talks, I guess my first bad dad joke is that we chose the name SELDM because that's how frequently you want to have stormwater quality problems. So our class objectives, we want to learn that SELDM and the highway runoff database are there, they exist and they're available for you to use. We want to go over what SELDM is, what it does. Hopefully you'll agree with me by the end of today that it's easy to use, you know, the highway runoff database and SELDM, and we'll figure out how you can find out more. So SELDM was developed by the U.S.GS in cooperation with the Federal Highway Administration to support, primarily support the NEPA process, so the National Environmental Policy Act. So whenever the federal government is involved in doing something, you know, and Federal Highway does that by paying state DOTs to build and improve highways, there's this proposed action and you have to do all this coordination and analysis. And then for each topic within the NEPA framework, you have to ask, will this project have a significant impact? So if it is no, you get to go to the categorical exclusion. If it's unknown, you do an environmental assessment. And if there is an impact, then you have to do an environmental impact statement, and then you say, well, what can I do to reduce the impact, like add a BMP or do some other action or some kind of compensation. So SELDM sits kind of here in this diamond. Is there a significant impact? So you can kind of get an initial planning level estimate to see, you know, if there's like very little risk of an impact, then, you know, you might be able to go to the categorical exclusion. If not, you can assess some of these other problems. So one example was there was this Iliana project between Illinois and Indiana, and I think they were widening a bridge. And it was a bridge over, it's like, I want to say the Missouri River or something like that. And it was a 5,000 square mile upstream basin, and they were just widening a bridge. So the question was, would this have an adverse effect? Well, in that case, you know, it's a huge basin and a teeny bridge. So it kind of common sense would tell you that, you know, there isn't going to be a problem, but the parties involved wanted to be sure. So they ran SELDM and it, you know, helped establish that categorical exclusion. So sometimes I call that model magic. Is there are some cases where common sense will let you know that, you know, it's not a problem, but sometimes if you have a model and it's simple, you know, it gives you a simple answer, it kind of quantifies common sense. All right, so SELDM was tested and reviewed by 43 professionals from USGS, EPA, Fish and Wildlife Service, and 16 state agencies. So that was 15 different people in 15 different DOTs and the Massachusetts Environmental Regulatory Agency, which is called the Department of Environmental Protection. So you can see, I think there's people from some of these states on the call today. So SELDM was designed as a highway model, but it can be used for other developed land covers. So these two schematics here kind of show you the whole idea of SELDM. Is you have like a site of interest, or, you know, in an urban basin, you might have sites of interest. But what you're worried about is what's the cumulative effect at this downstream point, which is shown as kind of the gray road on the left and kind of those two rectangles there on the right diagram. So you have this upstream area, and then you have the point of interest, and then you're worried about what's happening downstream. So SELDM does a lot of fancy math, but at the end of the day, it's a fairly simple mass balance model. So you have the upstream load, which is the upstream concentration, which is stochastic. That means it varies randomly, times the upstream storm flow, which is stochastic, it varies randomly. And then you have your runoff load from a highway or urban area, or it could be like a highway maintenance facility. So it's something that's discharging stormwater. So you have your concentration and storm flow from your road or urban area, and you can apply a BMP to that to reduce flows, concentrations, and loads of stuff coming off your site of interest. And then you have your downstream load is just the sum of the upstream load and the runoff load, and then the downstream flow is the upstream storm flow and the runoff storm flow from the site of interest, and your downstream concentration is just the load divided by the downstream storm flow. So in most cases, if it's a highway, it's not gonna be an undeveloped basin, it's gonna be whatever basin is above your site. But what we've done, in terms of like when you look at urban effects, if you want to see what's the cumulative effect of a bunch of different places on some downstream site, you kind of lump the areas together and you model them as, a single representative discharge. So SELDM has been used in TMDLs. We did a study for Caltrans where we came up with yields. That's pounds per acre, it's loads per unit acre. So then they can use GIS to figure out how much land they own and how much other, what are the other land covers and how much of this contaminant are they putting out, and figure out, where the state highway system fits in that basin. So this is the Willamette Basin in Oregon. And we did total phosphorus yields and multiplied those by the areas of the different land uses. And you can see the forests in that case were about 20% of the total annual phosphorus loads. Agriculture was almost half, and developed areas were about 30%. And the entire state highway system was only about 2.5%. So if in this basin they had to reduce phosphorus by 10%, you could rip out all the state highways and not get to your target. So the DOT alone could not, satisfy the TMDL. So SELDM is recommended method by the NCHRP, National Cooperative Highway Research Program, Report 918 for doing highway-related TMDLs. So I guess let's quickly talk about what we're doing with this class. So we're doing what's kind of known as a blended learning class. So I guess my last class, I said it was a beta test. I'm still trying to get the feel for how to run one of these off-site kind of web classes. It's more fun to get together someplace and do it in person. It's also easier to focus if you're in a classroom someplace away from distractions of your boss and your email and your desk. So what we'll be doing is doing some periodic webinars. I've sent you a list of YouTube videos. Don't get scared. You don't have to watch them all. You can decide which ones you want to watch. We have our SELDM webpage. Hopefully you folks were able to access that SharePoint server with the files. So that will have our class materials. And depending on how much you guys want to invest in time, we can do small group teams. Like if the Connecticut DOT people want to get together and like do a case study, they can do it. If Washington wants to do a little case study of a basin in their area, they can do it. And I think I scheduled this Thursday a couple hours if people wanted to make teams and kind of just play around with getting some answers. We could do that and talk about it. Homework, there's not really going to be any homework, but if people want to try stuff on their own, I can help facilitate that. And I guess the homework might be if you want more details and you want to be really learn how to use the model and what's behind it, you might want to watch some some of the YouTube videos, and then suggestions. I'm open to suggestions, what you guys think worked, what didn't. So, let me know as we go along. So if you want to dive deep, the focus of our online sessions together, I think, should be playing with and using the tools. When we did the live class, it was a 3-day class, 8 hours per day, with a lot of presentations and theories, but I think everyone's eyes were rolling back in their head. So it's better to, take it slow, spread it out, and maybe look at some of the different videos maybe as we come across them, or, at your leisure. So, yeah, so to become a SELDM expert, there's 2.36 hours, and don't take that mandatory seriously. Some things you guys will already know about, so you won't have to look at it. There's another 2.63 hours, and then I guess I haven't updated this slide, but with some of our webinars, there's I don't know if anyone added up the different videos in the views I played, but also this is, watching things in real time. So it is, if you speed it up, you can cut it in half almost. So if you look at the YouTube page, it may not always be clear, especially if you're looking at it on a phone, but each video has an explanation. So if you hit that little show more button there, it will, you'll get the full thing. So the show more, we tried to put in more information, but also the references. Like if you're interested in something in that video, if it's not a webinar, if it's, one of the teaching videos, it should have the references involved. So I guess you always hear the YouTube people say, what is it, subscribe and like or whatever, but yeah, if you want people to find it, you don't really have to subscribe. Very often, I don't think we can or should with our professional emails subscribe to things on YouTube. But yeah, I guess if you watch a video, just let it run through to the end. I think if you cut off early, that works against people finding the videos, and yeah, you don't really need to subscribe. And we also have the SELDM webpage. So the vanity link for that is www.usgs.gov/SELDM. The actual website name, it's this new Drupal system that's got these horrible long website names. But I can send you the full-time link if it's not already in the material I sent. We have in reverse chronological order all the different reports. So if you're interested in TMDLs, you can go look at, the TMDL report we did for Caltrans is pretty short, and we've done different studies. If you're interested at, what is background stormwater? What we found when we've done simulations is that natural background stormwater from undeveloped basins don't meet water quality criteria for phosphorus. Just naturally with the sediment and the sediment and phosphorus with the resuspension and wash off, so I'm wondering if some of these listed streams might be just listed because somebody measured during an event, whereas most of the water quality criteria are for like the 7-day low flow because, they were set up for regulating wastewater treatment plants. So they may not be well suited to stormwater. But I guess that's more of an editorial at this point. And so, like I've kind of been alluding to, you can decide how involved you want to be with this class. You can just kind of sit on the couch and watch us go through stuff and kind of get a good idea. That will give you an idea about what SELDM can do. If you want to become an expert SELDM modeler, you can put in the effort like Sarah Flanagan, run the distance, watch all the videos, et cetera, et cetera. So most people kind of end up somewhere in between. So let's see, I'll stop this presentation and start the next one. I guess if you have comments going along, feel free to put them in the chat. And we'll we'll talk about the information once we get through the next talk. Unfortunately, did I just make that sound like it's a punishment? So this will be just the overview. SELDM provides concentrations, flows, and loads. As we discussed before, we wanted SELDM to be accepted by regulators and decision makers, and we wanted to build an application that people could use. So what we did is we worked with a bunch of state DOTs, people from the Fish and Wildlife Service, the Massachusetts Department of Environmental Protection, and then we had a number of people from the U.S. EPA Office of Water, mainly in DC, but I think some of them were in the Western region. And so we had people weigh in, so we'd build a tool that people could use and that people would accept. So what is SELDM? So SELDM is the stochastical empirical loading and dilution model. So it's stochastic because it uses Monte Carlo methods to create a sample of events representing the combinations of flows, loads, and concentrations that might occur over a long period of time. So what SELDM does is it generates a whole bunch of random numbers and then applies those numbers using statistics for each variable to create these populations of storm events. And each storm event has precipitation, it has upstream flow, it has water quality from the upstream basin and from the highway. BMP performance varies randomly. So what happens is you run a bunch of these storms. Usually it's between 1 and 2,000 events get generated that represent like 20, in kind of regularly humid areas, it's usually 20 to 30. If you go out to like a desert site, you might get like a 50-year record because there's so few storms per year. Now it's empirical. What that means is it's based on data and statistics rather than theory. So I guess my go-to example for that is if you look at something like swim, it uses this modified Stokes equation, and Stokes equation is the theory, which if you had perfect knowledge of the system, you could do that properly. But what we found is that grain size distributions and densities vary by orders of magnitude within and between storm events. Temperatures change, so viscosity changes during events. So the treatment, trying to deterministically figure out what's going on to the level of detail that that's meaningful could be difficult. So what SELDM does is it uses treatment statistics from the international BMP database, inputs versus outputs. So the variation, we're not using the same treatment every storm. Again, it's randomly generated based on actual data. So SELDM isn't calibrated like other models where you're trying to match a history. So for SELDM, you pick good statistics and the model calibrates itself. So it's the statistics that you choose that gets your answer versus history matching. The problem with history matching models is what happened in the past is not necessarily what's going to happen in the future. And the biggest problem with history matching is it's very rare that you go out to a site and have data at a given site. So in Southern New England, we looked and there was 48,000 road stream crossings. And we had highway runoff data from about 14 sites. And we were able to dig up good water quality data for about 84 sites in all of Southern New England. So you could say if you were rolling a dice, the chance of having your issue be at a given stream crossing and having it have the data that you need would be, very slim. So that's what SELDM does for you. You can use the representative statistics from other sites to try and figure out what might go on at the site you're looking at. So it's a loading model. It provides storm and annual loads. So that's what's kind of good for the TMDL analysis. And finally, it's a dilution model because it does that mixing of the upstream and highway to indicate the chance of exceeding some target value, some adverse effect value. So I kind of covered this in the intro, but we'll talk about it again because it's important. So SELDM uses just a simple mass balance approach to calculate these flows, concentrations, and loads by storm and by year. So again, you have the upstream load. It's this random population of concentrations, random population of storm flows from the upstream basin. You have it from the highway, or again, if you have an urban area or a highway maintenance facility that's discharging to a stream. So again, you have these concentrations and storm flows with and without BMPs, and they add the components together to get the downstream loads and flows, and you divide the load by the flow, and you get that population of downstream concentrations. So by getting a population, you can then assess what's the risk of exceeding, this water quality criterion, or this, this loading level I don't want to exceed. All right, because it was designed for NEPA, but it's also useful elsewhere, SELDM is designed to facilitate what's known as scenario tests and sensitivity analyses. So a scenario test might be, I have a highway going over 5 streams, so I want to look at what's happening on each stream, whereas the sensitivity analysis might be, let's say I have a high, medium, and low highway runoff concentrations from these 3 other sites, and I don't know which one maybe I want to use. So I could run 3 simulations where everything else is different, is the same, except I vary the concentrations and say, oh, how important is that concentration in the input concentration statistic in affecting the answer that I get. So SELDM has the organization of putting in doing the work in SELDM is, first you have a project. Now a project could be an actual highway project that might have several outfalls, or a project that you might be saying, oh, I have different alignments I want to try. Or like I said, you might be saying, well, if I do this or that, or if I have the pre-development condition, or the, before I add a lane to this site and after I add a lane, those would be 2 conditions that might be under a project. So those things I were describing are what's known in SELDM as analyses. So each analysis is all the information you need to run a scenario. And then each analysis can run one-to-many constituents. So a constituent is like, lead, cadmium, copper, pH, whatever your water quality constituent is. And for that, you have your highway constituent, your background, your BMP, and from that, you get your concentrations and loads. So yeah, so you put in your project, you can have one-to-many analysis, and in each analysis, you can have one-to-many constituents. So once you set up an analysis with everything you need, typically we go and we copy that and then make modifications to that to test different things. So SELDM was designed to support the environmental decision-making process. So what we want to do is have kind of a tiered analysis. So like I mentioned, the bridge over the 5,000 square mile river. You may not want to expend 3 weeks of work to get to the point of, well, you should never spend 3 weeks of work doing one SELDM analysis. Hopefully you'll see that. But, I guess being a little hyperbolic, but you don't want to spend a lot of time at sites that may not, that have a really remote chance of having a problem. You want to more focus on sites that might have a problem and what can you do to mitigate or eliminate that problem at that site. So SELDM has this first level analysis where you have regional inputs. This is based on hydrologic similarity. So you're saying sites within a region are similar to the regional values. So SELDM, we use the level 3 EPA ecoregions as one of our regions for pre-storm flow, precipitation, and water quality. In the U.S., water quality is QW for some weird reason. You also can use rain zones. The EPA 15, EPA has 15 rain zones across the country. Ecoregions tend to be, a little smaller, more focused. So we rarely use the rain zones themselves. So level 1 analysis, you just pick available background information that's already in SELDM and you just run through. And if it's like, okay, there's a very small chance that I'm going to have an adverse effect here, that's where you could go to that categorical exclusion. The second level might be, let's say you have, it's a sensitive site, or you've run the regional analysis and it's like, oh, maybe we do have a problem here that we have to look at. So that's where you use data from nearby sites. You need a little more information and make a few more engineering judgments about, what's the best data to use. But again, it's hydrologic similarity. We're looking at data from nearby stream gauges and rain gauges that represent what's happening at the site. Again, and proximity. Sometimes, like particularly in mountainous areas, the nearest rain gauge might not be the representative rain gauge because you're on the other side of the, you might be a mile away, but you're on the other side, the dry side of the mountain, or your elevation may be different. So the cost of going to the second level analysis is you need to know a little bit more about your area and your site of interest. And then a third level analysis, that's where you put in your own user-defined statistics, for data you've collected on site. Or, if you have more generalized data, you can use those statistics. The problem with the third level analysis, well, why don't we just go right to that, collect data on site and get a more exact answer? The problem is data is expensive and it takes a while to collect. It could delay things for a year or two. And if you have a remote chance of having an effect there, that might not be time and money well spent. And yes, I guess I've already covered both delays and whatnot. So there's the 3 level of analyses. So SELDM is a water quality model, and it's kind of a basic hydrology model. So what happens in this diagram shows how we get from precipitation events to the different flows that we need. So the top box here says storm event statistics. So SELDM uses the EPA definitions of a runoff generating event. It generates some of these random numbers, you apply it to the statistics and you generate this series of events. So what happens is the same precipitation, the same events occur to the upstream basin and the highway site. So for the highway site, we generate a bunch of runoff coefficient statistics. So it's not the same runoff coefficient in every storm. The runoff coefficient statistics, you can put in your own, but generally they're associated with the imperviousness of your highway and your upstream basin sites. So precipitation times runoff coefficients get you your highway runoff flows. For your upstream basin, there's 2 components. You have the pre-storm stream flow. So what's in the river before the runoff starts. And again, kind of similar to the highway runoff site is you have runoff coefficients based on the upstream imperviousness. And so the precipitation gets, the input precipitation varies randomly to get the flow. So your upstream flow is the pre-storm flow plus your runoff hydrograph, and you add the upstream and highway runoff flows together and get the downstream flow statistics. So it's fairly basic in that it's, basic mass balance, addition, subtraction, and division. The power comes from statistically representing, the hydrology of the system. So we didn't want to build a model that was tough to run. So we did a lot of the work for you. You need statistics to run SELDM, but we've calculated them and we made SELDM a database application. So all the information will be there for you. You know, you can click and, you know, on things to pick them. So there's like drop-down lists. So this image shows our precipitation stations. The pastel polygons are the 84 U.S.C. EPA level 3 ecoregions, and these black line polygons are the 15 EPA rain zones. So I generally go to Nevada to talk about this because you know, there's a low density of rain gauges there. But if you can see where my mouse is circling, you can see we're in rain zone 11, which covers a lot of ground, but a lot of arid ground kind of inland there. This kind of pinkish pastel ecoregion is the basin and range ecoregion. So if I was in this area of Nevada where you can kind of see these 3 rain gauges, I could either say I would either use the average or median of statistics from rain zone 11, from the basin and range ecoregion, which would be the average of all these dots. Or if my site's here, I could say my site is most like one of these 3 dots, or I could take the average and median of the 3 dots. And so that would be the level 2 analysis, where I would pick, you know, a few of these rain gauges that might be representative of what's going on in my area. So similarly, we did statistics for you from 2,783 stream gauges and preloaded them into SELDM. After SELDM was developed, we did statistics for about 20,000 stream gauges nationwide. So if you go to stream stats in your state and click on a stream gauge, you will get the SELDM statistics for that stream gauge. And you could, you know, you could enter those into SELDM. So similarly, we didn't use rain zones for stream flow, but if you look at Nevada, you can see this little cluster of sites in the middle of the state here. If I'm in this area, I can either use the average of the basin and range stream gauges, or I can take the average of it. Looks like there's 4 stream gauges here. Or, you know, I could pick 1 or 4 of these to try and get my stream flow statistics for this site of interest. For background water quality statistics, we did data mining from the USGS National Information System, and we've got about 2 million samples from 24,581 water quality monitoring stations nationwide. So unfortunately, not everything was measured in every station. I think total phosphorus and suspended sediment are the top 2 nationwide. About 30% of these stations have one or both of those constituents. Once you start looking at like total metals, you get down to like about 10% of these stations nationwide might have copper, if you're interested in copper. I guess back to hydrology from water quality. So SELDM is generating these events. It's generating the pre-storm flow. So when we look at a runoff hydrograph, it also simulates the timing of runoff, but it does it in a fairly simple manner. It uses a triangular runoff hydrograph. So we can see in this diagram on the left, we see runoff volume and time. So the pre-storm upstream flow stays constant, and we have this triangular upstream runoff. So that's the duration of the runoff hydrograph, and that depends on the length and slope of the stream basin and the imperviousness of the upstream basin. And then if we look at the lower left, let's imagine that these are 2 runoff hydrographs. The short, sharp peaked one is highway runoff, and then this longer, lower triangular one might be if you put in a BMP. So we can see if you have this upstream runoff hydrograph and you have the highway runoff, you get to this duration 1, you're only in the rising limb of the hydrograph, whereas if you put in a BMP that stretched out the hydrograph from the highway, you get out to duration 2, so you get more dilution. So, we didn't want to cheat and say, oh, the highway gets all the dilution from the upstream basin. It just gets that portion that would, arrive while the highway was discharging. The highway is usually these short basins that maybe run, an hour, by and large, minutes to an hour after rain stop. Whereas, even a 10 square mile basin, the hydrograph, after the rain stops, the storm event hydrograph may continue for hours to days, depending on the basin afterwards. So what we see is if we look at the percentage of upstream flow for this duration 1 and duration 2, you can say that, this is just a purely hypothetical example, but just the raw highway runoff for this hydrograph, you're only getting about 15% of the upstream flow to dilute your highway runoff into, versus if you put in a BMP that stretches out the hydrograph, the outflow hydrograph from the highway site, you might get up to like 55%. And again, these are just generalized example numbers. Everything depends on your BMP and your site properties. But it's not the same for every storm. The basin lag is the same for every storm, but the runoff hydrograph from each storm, there's a random component to that too, as to represent the variation that we see out in the actual world. So SELDM was developed as a highway runoff model, but it can be used for many types of sites. So when we go to put in our highway site, SELDM is simple to use because it's just got these 5 properties that we think about, and actually it's really only 4 properties. So what we need is drainage area. So, this picture of these 2 bridges on the Charles River, we see the drainage area is encompassed by if only the bridges are draining to the stream, is encompassed by these 2 yellow polygons. To get the timing of the runoff from the highway, we use the main channel length and slope. So for a bridge, the main channel is going to be from the crown of the road to the scuppers, and then the slope is going to be the camber of the road from the crown to the scuppers. So the other thing we look at is the imperviousness to get the runoff coefficient statistics, and we see, well, the bridge is 100% impervious. And then we kind of look at this and we look at like a literal site and a conceptual or hypothetical site, I guess. When the people are worried about water quality in this stream, they're not necessarily worried about what's happening between these 2 bridges on the same highway. They're more likely worried what's happening downstream of both bridges. So when we simulated this, what we would do is add these areas together and get kind of a characteristic length and slope and imperviousness to kind of get the net effect of what's going to happen down here downstream of both these bridges. Now, when we set up SELDM, we set it up for the basin development factor, but over the years, we found that imperviousness is easier to explain and to use. So the basin development factor is just kind of a gauge of how much engineered drainage structure is in the highway and the upstream basin. But if, anyone who's younger, if I use the term cheat code, they'd know, it's like in a video game, you use something to kind of get away from doing something. So that's a pretty poor example. But if you just put a -1 in for the basin development factor, it uses imperviousness to get the timing of runoff from the site. So SELDM can be used to model the pre-development conditions. So if you have some forest runoff quality, you can simulate the forest site. If there's water quality problems, so if the question is, I'm going to put a highway in here, what's it going to do to the downstream water quality? You can run the upstream plus this forested area and see what's going to happen. What's the risk of exceeding the water quality criteria, and then you can come through and simulate your highway area, or let's say this was a mall somebody was putting in, or whatever action they want to do, they'd be able to run what is the water quality after you make this change to the basin. So again, it's just a drainage area. imperviousness, the length of the main channel, and the slope, the main channel slope between points that are 10 and 85% up the channel. Similarly, if we look at this mall, the mall may have roof drains and all these contributing drains. With SELDM, you just need the drainage area, the imperviousness, which, you know, it looks like there's some tree islands here, so that might be 99%. But again, we're just looking at the main channel length, which is this light blue line up to the high point, and we look at the slope difference from, you know, 10 to 85% up the main channel. We wouldn't, let's say there's a roof drain and you got just a vertical drop down into the sewer system, you wouldn't really count that part of the fall because, you know, the flow is instantaneous. But again, we just have a couple basic basin properties which are easy to figure out or kind of get an approximation for. And one might think, oh, you know, this is too simple. Look at all these stormwater drainage systems. But this is the approach that's used for the national flood frequency equations. So, you know, it's not a perfect representation, but it's been shown, you know, that the main channel length and slope have the greatest effect on the timing of the whole hydrograph. So today, hopefully we'll get through a case study. It will be Hard Brook. It's a 1.34 square mile basin in Northborough, Mass, near where my office is. So we're going to be trying to run SELDM with this section of 290, which is within the blue polygon, and it stretches from drainage divide to drainage divide, and we're assuming all this area gets into the stream right here. And then this is an image from an older version of Stream Stats where the black line is the basin divide and the red line here is the main channel. So when you run SELDM, it generates, like I said, thousands of storms, or 1 to 2,000 storms. This is for Southern Massachusetts. We used highway runoff database information from a Massachusetts study. So we put these statistics for these highway runoff sites in SELDM. It runs all these events and we get this population. So when you're looking at this graph, the vertical axis is total phosphorus on a log scale. The horizontal axis is a probability axis. So you can see it's kind of weird that like 98 and 99.5 are close, but you go to 99.99, there's a large space. So probability axis stretches out the extremes because that's usually what we're worried about. So the gray circles are the highway runoff. So this is total phosphorus from the pavement surface. So we could see, you know, rarely we might get up to 1 milligram per liter from the pavement surface. And then, you know, in a few storms, we get down below 0.01. So that might be, we're not simulating individual storms, but conceptually that could be you have a gully washer that, you know, rinses off the highway, then you have another event afterwards and there's not much buildup on the highway. So you could get low concentrations. So these yellow diamonds are the concentrations that you would get out of a grassy swale. So we can see that the grassy swale doesn't do a huge, doesn't make a huge difference in the concentrations. And down when highway runoff concentrations are low, the grassy swale could be higher than the highway runoff concentration. And that makes sense. If you have quote unquote clean pavement and the runoff's coming off the pavement and it's running over grass and dirt in a swale, you might tend to pick up some phosphorus. Now, one thing we see here that looks weird is why do we have this horizontal line of equal concentrations? What SELDM does is it includes the what's called the minimum irreducible concentration, and you can set that. In this case, it was like 0.015 or something like that. And basically what that represents is that you are not going to get distilled water out of a grassy swale. So there's kind of some lower limit that people have looked in the literature using various ways to say different types of BMPs can only get the water so clean. So EPA was on board for this, that we just kind of put a lower limit on the ability of the BMP to reduce concentrations. So once we generate this population, what information does that give us? So if we look at these horizontal lines, we can see that this white line, this white horizontal line at 0.02375, that's the EPA criterion for the Northeast region for natural waters. And then we see the yellow line is 0.1 milligram per liter. That's again receiving water, the long time receiving water standard for waters that flow into lakes and ponds. And then what we see, this red line up here, is effluent limits that EPA expects from wastewater treatment plants or small wastewater treatment plants. So obviously highways can't build a wastewater treatment plant, like a municipal wastewater treatment plant at every road crossing. So, this concentration looks high, but this is, still perhaps maybe ambitious to try and hit this. So what we can see is with these gray dots and the yellow lines, that if you're going to try and apply this ultra low receiving water standard to highway runoff or BMP discharge, you're never going to get there, because more than 95% of the time, these are going to exceed that concentration. So that's the risk of exceedance. If you try and apply the in-stream standard to runoff or BMP discharge, we can see that highway runoff is going to exceed this 0.1 milligram per liter probably about 50% of the time, and the grassy swale is probably going to exceed it about 40% of the time. So EPA historically has looked at like a 1 in 3 year event to worry about, what's going to happen to the ecology of the stream. So if you're exceeding this amount every other storm, what it just says is that with highway runoff from this, from these statistics, or with the commonly used BMP, you're just not going to get there. And however, if you go to if you apply the same standard they're applying to municipal dischargers to the highway, you can see highway runoff is going to exceed that maybe 3% of the time, but if you put in a grassy swale, it drops it down to about 1% of the time. So the grassy, in terms of concentration in the effluent, the next question is obviously, what's it going to do in the stream? So SELDM gives you that information as well. So SELDM provides background water quality concentrations, and you can simulate that. So what we have here is the blue stop sign here are the regional values in SELDM for total phosphorus in the Northeast region, Northeastern coastal zone. And we see there's these different stream basins that we have data for. This one down here is actually the lowest one, is the outflow from a large drinking water reservoir. So it's like as if they had a big wet pond treatment with a 6-month residence time. And this is the phosphorus you would get from that. So again, we simulate all these events with the available statistics, and what we get is this population of events. So we can see that based on regional statistics and these 3 streams shown in yellow, if you're applying that 0.02375 milligrams per liter, even the best stream is going to exceed that about 70% of the time. The regional values would estimate about 85 to 90% of the time, and then this one tributary exceeds this standard more than 99.5% of the time. If you jump up to that 0.1 standard for receiving waters, and again, that was based on wastewater treatment plants, so that was based on low flows when you didn't have a lot of natural phosphorus in the stream. But this worst stream is going to exceed that 0.1 standard about 75% of the time, and the best stream is still, with that, downstream of a drinking water reservoir, is still going to exceed 0.1 about 10%. Well, I shouldn't say of the time, about 10% of storm events. So this is during storm event discharges. Each of these is an event. So in about 10% of events, this this reservoir basin is going to be putting out more than that 0.1 milligram per liter. All right, and so what we're showing here, we just showed you highway, then we showed you upstream, and this is what happens downstream. So again, we have our total phosphorus on a log scale, we have our probability scale. The blue stop signs are upstream, and then the green triangle that points upward is downstream concentration without a BMP. The yellow triangle pointing downward is the downstream concentration with a grassy swale, and the highway runoff concentrations are gray. So we can see that, you know, at the lower concentration from, you know, green to yellow, there is a shift from left to right. So you're reducing the probability of exceeding, but you can see that, well, one, that the highway runoff concentrations aren't that much greater than background concentrations, and that, you know, there is a shift, but you're still exceeding this lower standard 90% of the time. You go to 0.1, we can see that the highway exceeds more, but we could see that the upstream, downstream, with and without BMP isn't making a big difference. And then you just follow the probabilities up to the highest concentration. You can see at this site, putting in a BMP is not going to make a big difference for total phosphorus. So, you know, if you only have so much money to put in BMPs, you might be wasting your money here. That's not to say that, you know, for total copper, it might be a totally different story. You know, depending on the constituent, if the highway is a lot higher and the background concentrations are a lot lower for total copper, you might get the case where, you know, the highway really bumps up the concentrations without the BMP. All right, and so this is a schematic of the Scituate Basin. And so when we're talking about sites, if you're looking at annual loads or a lake analysis, your highway site can be more hypothetical because you're not looking at event by event. So you're not worried about the timing of runoff for individual events. So if you had like a reservoir basin, or, you know, if you're looking for, let's say if this was an estuary and you were looking for the total highway runoff concentration of some constituent, then you would use, you know, maybe the whole highway area. So in the Scituate Basin in Rhode Island, if we're looking at chloride, for example, well, when chloride gets into the groundwater, it gets into the Scituate Reservoir sooner or later. So if we're looking at long-term, you know, loads and yields, and, you know, what's going to happen over a long, long period of time, we'd probably use the whole road network area to figure out how much chloride is going to end up in the Scituate Reservoir. However, if we were looking at total phosphorus, and phosphorus tends to get bound up by the, you know, the soils and sediments and aquifer sediments. So in that case, we may not use this whole area of the road highway network in the basin. We may only clip out the areas that we can show are contributing to the streams flowing into the Scituate. So the areas, you know, what they call country drainage, those areas of the road that don't drain to a surface water body, we might cut those out and not use those. So that's where we get kind of this literal area would be all the roads in this basin, but the effective area is, you know, you may only use certain parts. So to do this, what we do, and what Mass Highway has done out on Cape Cod, is we run the loads per acre over the long period of time. So you get a yield, so pounds per acre per year. And then they use GIS to figure out, you know, what their area is in acres. So you multiply your load in pounds per acres per year times acres, and you get, you know, what is the highway load in this basin in pounds per year. So again, SELDM's a stochastic model. So you're not getting just one answer, you're getting this population of answers. So this is, again, a probability axis, but in this case, it's annual loads. So it's pounds per acre or yields. but this is per year. So we have this 30-year period. We can see that there's large variations in total phosphorus, mainly based on having, wet years and dry years, how much volume is coming off the highway. And we can see that the highway runoff is about twice the grassy swale loads. And what's happening here is that the swale tends to knock down high concentrations, but not low concentrations. So you're reducing the worst concentrations, and the swale, although it's not it doesn't do a fantastic job reducing concentrations. You're getting some good infiltration. So between knocking down the highest concentrations that you would see and knocking down the flows, you get like a 50% reduction in load. So SELDM is kind of good at, if you look at the International BMP database, they do a great job of looking at concentrations, but they don't really address loads. So SELDM helps you put all that information together to get a better answer. All right, SELDM has a graphical user interface with a series of forms. So because it started out kind of in the NEPA world, we have documentation. So we have an analyst. If you look at an environmental impact statement, there's a whole section on who did the analysis. So we have the analyst where people can put as much or as little information in as they want. Again, we have the project. A project could be a literal project, or if you think about a project is a drawer in a filing cabinet containing related information. And an analysis is a literal analysis, but you can also think of it as like a folder in that drawer that handles related information in the filing cabinet. So your project is your drawer, your analysis is your folder. You can go through the process and specify everything and then go back and copy it and then just change different things. So those are your three documentation forms. Then you get into your site and region forms. You have your highway, your grid, your ecoregion, and your upstream basin. If you're doing a lake analysis, you also may have a lake basin to specify. Then you get on your hydrology forms. You select your precipitation, your stream flow, and your runoff coefficients. And then you get into your water quality forms where you pick your highway, your upstream and downstream water quality, and then you put in your BMP and run the analysis. So going through this, once you get comfortable with it, you can do a SELDM analysis probably in 15 minutes. Actually, running the model only takes about a minute and a half. All right, so let's see, I'm gonna pause recording.
This conference will now be recorded.
Okay, great. So SELDM is a database application. We did that so that you wouldn't get bogged down building these complex input files or entering a huge amount of data or statistics. And once you set something up, it would be self-contained. So if you're doing something that somebody else has to review, you can give them this one file and it should run for them as it runs for you. So when you open up SELDM, it's a Microsoft Access database application. And you can see it's got this little cute opening screen. It gives you information about the version. If you click this button, we have our explanation. So one thing is, consistently, well, we can see here, it comes up and it's highlighted this way because, so you can copy it in. You can go large font, which is just kind of a toy, I guess. But as you move through, if you have to write a report, you can copy stuff right out of the explanations and use that to, if you have a report. So this just talks about SELDM itself, but I'll show you more as we get in. SELDM, the newer versions of SELDM now have a batch run process. So if you can kind of quote unquote super users can set up in a lot of input and then import it into Access and then run a bunch all at once. For the North Carolina decision-making system, I worked with the people down there and they ran SELDM like 100,000 times. And then for the Southern New England study, I forget, we ran it like 12,000 times because we were doing all these sensitivity analysis to look at all these variables. Typically, for a given project, you run it manually and you can run it like once and use that answer, or you could run the same thing several times and see what's, the stochastic variability might happen to you or might do to your results. So when you open this up, if you're going to do it manually, you just hit proceed. And then you come to this analyst identification. It's not really a login, but you can kind of get the feel. So when you look at SELDM, once you enter something, it's available in this drop-down list. So we try to use common themes as we went through the graphical user interface. So typically when you come onto a form, you see select is the default. So you select from what's available to you. You can edit things. So see, once I hit edit, all these fields became live. So this is more for an environmental impact statement. So you can put in the information about the analyst, the role, primary, secondary, reviewer, examiner, and each of these SELDM projects can have multiple analysts. So you can put in address, information, contact, and any notes. And I think I've seen in some EISs, there's like mini little resumes that says why you're worthy to do an EIS. But so typically we do anonymous. In some of the, like the California TMDL one, if you go to the site, you can download the California application that's preloaded with California water quality, and you can click through there. And I think that one might say USGS instead of anonymous. So you can see once I've said edit or clicked edit, I've got this choice to accept updates. So until I click that, any changes I make here are not retained. And then if I enter a new analyst, we could see that the select is grayed out, and then I would type in a new analyst, and once I click accept updates, that analyst would be available from the drop-down list. So I'm just going to go forward with anonymous. So we can see, right, SELDM comes with this example project, which was the 1990s federal highway study site. If you go to the North Carolina application, they've got a bunch of North Carolina projects. If you go to the Caltrans SELDM application, there's a bunch of projects to look at different TMDLs and to look at general numbers. And then the Southern New England SELDM has a number of projects as well. So right now I'm going to enter a new project. So I just click enter new, and we'll just give it. So when you go through the interface, you can see that there's a little asterisk under general project information, system variables. And you can see on this tab, project short title has an asterisk and it's bold. So only the things that are bold and have asterisks are required. So let's just call this fall 2022 class. That'll be a project. I don't need to put any of this. This project ID number, again, if you're doing an environmental impact statement or maybe an EA, there might be some official project number for the change, the highway change that you're doing. This one is starred, but these variables are preset. We did the USGS National GIS grid, and we used the EPA level 3 ecoregions and the 15 zone map. Right now, that's all that's in there. But if you want to have a state specific grid, if you want let's say you want in your state, you want to use level 4 ecoregions, you could add those to the database, and then that would be available on the drop-down list. And then the project abstract. A lot of the variables you put in have this abstract. This is an unlimited length field, so you can put as much or as little or zero information in as possible. What you put into these fields will come out in the outputs. So yeah, so this might be, you know, why are we doing this highway expansion or this new highway segment? Any information that you might want to have documented with, you know, with your outputs. All right, so so you see for the project, all I needed was a short name. That's the minimum required. All right, and you see now that I've entered this new one, I've got two choices. I can either do the example project or I can do the fall 2020 class. And by switching those, you can see it automatically populates. So now that we've set the 2022 class under project, we're going to go to the analysis. And so again, there's no analyses available under this project, so there's nothing to pick. And we have to start with enter new. So we'll do Howard Brook. And we'll just give it a version 1. Default total phosphorus. So draft, final, supplemental, that's EIS language. It doesn't really matter. I guess you could put final. This is the master random seed. More information is available here. We talk about that a little bit in the California and Southern New England reports. Yes, so I should say that you can see as you go through the interface, we have these, you know, the question marks will bring you information about what's there. Some of it's a little rudimentary, like drainage area is the drainage area. So what are we going to do? We can either do a stream and lake, or lake basin output. Right now, we're just going to, Howard Brook is a stream basin. So we're just going to pick that. And again, I can put as much information as I want in here about this analysis description. So if this was like a real analysis, and let's say you were testing 3 different highway alignments, you might want to say, you know, why is this analysis? You know, what are we doing with this one? You can see we do have the short name is 50 characters. That's what gets up in this selection box. The short title or short name, and then our short description is 250 characters. Usually you can put enough in there so people know what's going on. So now we're just going to accept updates. So there we are, Howard Brook V1. Now we have an active dropdown, but we only have one choice because we've only picked one. Now, if I come to the information button up here, we can see that it's just a basic, what is an analysis? That's the information that it provides. But we can see this analysis status. So as you go through and define an analysis, here's the different things that we're going to specify. And as we specify them, these little boxes will get checked. So what this does for you, it's kind of a check as you're going through, like, oh no, where am I in the process? But it's also, if you've specified an analysis, but you want to change one thing to see what happens when I change this one thing, you make sure that you've gone all the way through the analysis and then change that one thing. So we'll close this form, close the form. And I guess, yeah, maybe we'll, let's edit this one and call it swale, because we can quickly, Howard Brook swale, accept updates. So now you can see now it's Howard Brook swale is the name. Okay, so your highway site characteristics. Let's see, hopefully I left some of, so let's see, in the folder that I directed you to, there was a folder that was called First Run. And we could see that there's class exercise. So this is a presentation, but I wasn't going to give it, but let's see. So basically, I showed you the map of, you know, I-290 and Howard Brook. Basically, what we did was, and in most areas, if the highway is existing, you can go to Google Earth and you can kind of use the measuring tools on Google Earth. And we can go through that on Thursday if people want to dive deeper. But you can get kind of, you know, hopefully you have highway plans, but if you don't, you can kind of use Google Earth to figure out what your highway site looks like. So what we end up with basin properties for the highway are, we have this latitude and longitude. We have an area, channel length, slope, impervious fraction, and originally we did this basin development factor, but we're going to use that cheat code to use imperviousness for our basin development factor. If you open up the class example, Howard Brook, we've got all the variables that we'll be using in terms of basin variables and water quality, etc. So I'm going to move this off the screen. Well, actually, I could probably fit them both, right? Maybe not. But if you open that file, class example, Howard Brook variables. So if I do, my name is I-290 at Howard Brook. That's my short name. I can copy this. Now, if you guys use like, if it's an existing highway and you have like mile marker or, you know, whatever coordinate system you want to use, that could be part of the site name. So I'm just pasting in my latitude and longitude from that file. Now this latitude and longitude, I put in precise values typically so that you can click on a point on StreamStats and get the same answers. But in reality, your latitude and longitude only need to be within, like, I don't know if I'm aging myself, but you know, within a USGS quad sheet, like you just need to be within like a quarter of a degree. But for documentary purposes, it's good to get, you know, the exact point where the stream will cross the road. And now, you know, nowadays with like Google Earth, it's pretty easy to get those, you know, those locations. So for hydraulics, we have our drainage area in acres. So the highway is 6.4 acres. The drainage length is 2,767 feet. The mean basin slope is 71 feet per mile. Now, what we're worried about is the highway runoff. So we're going to use the pavement area. So it's going to have an impervious fraction of 1. We're using the paved area. The grassy swales are going to be our BMP. And as I said, we're going to use the cheat code, and I think it's listed here. But if we add a -1, it's going to use, rather than coming up with this basin development factor, if we use a -1, it's going to use the imperviousness to do the timing of the hydrograph. Now you can see that name and location and hydraulics have the asterisk. This other and site description do not. But if it's a highway, you can put in lanes, lane width, feet, site, you know, site description is again one of these memo fields you can put in as much as you want. Now we could put I-290, if we were doing a change at this highway, adding a lane, we could do I-290 before, and then I-90, I-290 after, or with an extra lane, or however you want to say it, so that you could do this site and then do it, see what happens with the current site and see what happens if you widen the highway. So if we hit accept updates here, oh, which one? Okay, so this one just says you specified a basin development factor BDF of -1. The basin lag equation using the basin lag factor and imperviousness will be used. So that just confirms that we used the cheat code. So I have I-290 at Howard Brook. If I'm right here in the site form and I know I'm going to add a lane on each side, what I can do is I can copy this, and it gives me the instructions for copying, and I would so it comes up, so I'd say, or I guess that might be it. So we're adding lanes. So the location would be the same. The length, the slope, the impervious fraction, the BDF would, basin development factor of -1 would be the same. We're just increasing the area. So let's see. I guess if we look at, so I-290 is a 3-lane highway with the breakdown lane. So basically adding, so that's like 1, 2, 3, basically just simply that's 4. So if we look at 5/4, so it's 1.25 times the area, and our original area was 6.4. So if we add 2 lanes, we're going to end up with 8 acres of highway pavement draining to this. So I've entered all this, but it doesn't take effect until I click this copy site. And again, it just tells me I used the -1. So we're just going to go through here with the original highway, and we'll hit proceed. So I guess if I looked at this, you could see that what did we just do? We just defined a new one, and then we copied it and just modified the thing that we're going to change. So this is a nerd form. It's just the review geographic information grid specifications. So what people usually forget is they forget to put the minus on the longitude. So you end up over on the other side of the world, and we don't have precipitation or stream flow data over there. So, or water quality, or, well, I guess they probably have their own ecoregions. But if you come to this form and there's a big red error message that says you're outside the grid, then you just have to modify your latitude and longitude to get inside the grid. And again, usually it's that this number, the longitude, has to be a negative number. Okay, the next thing you get is your ecoregion form. So when you put in your latitude and longitude, you automatically get the ecoregion that you're supposed to be in. And we can see that if you come to this tab, neighboring ecoregion, you can see that we're surrounded by 59s, but up to the upper left, you're into that northeastern highlands ecoregion. So if my latitude and longitude was here, but I think that my basin is more characteristic of the highlands, I might manually choose or specify that I'm in that ecoregion rather than this ecoregion. If I do that, it will give, it will give me a warning. But for the purposes of today, we're going to keep going with the default ecoregion based on our input latitude, longitude. The other thing that might happen is to select the ecoregion, we're doing everything on a 0.25 degree grid square, so a 1/4 of a degree latitude and longitude. The original ecoregions, you know, if you look at the map, they're lines, they're not gridded. But I talked to Dr. Almernick, the guy over, I forget which agency he's from, but he said, you know, we made lines on the map for the ecoregions, but they're not really strong boundaries in most places. They're just kind of diffuse, amorphous transitions between one ecoregion to the other. So even though we might be on a line, you know, the case for choosing another one might be that you feel like you're in that other ecoregion. All right, we've selected the ecoregion, so we proceed. So if I forgot something again, just to I can go back to the previous. If I've made a mistake on something, I can go back and it without accepting, and it will like get rid of my choice. So right now, we're going to specify the upstream basin. And again, if we look at either the stream stats output that we gave, let's see. Let's see, here's the stream stats report. It gives you the drainage area, the slope, and the length of the longest flow path. Or in that directory I put up on the file share site, we have our upstream basin properties. So we have our area is 1.34 square miles. Our main channel length was 12,619 feet. Our slope was 150 feet per mile. And our impervious fraction is 0.041. And this basin development factor, we're going to use that -1. So I'll put this over to the other screen and just copy the values in here. So this would be Howard Brook at I-290. And again, I can put in these just full names, brief descriptions. They're not required. So what do I need? I need a drainage area. A length in feet. A slope in feet per mile. And impervious fraction. And again, our basin development factor is going to be a -1. Okay, for the upstream basin, we also needed to give information about the hydrograph shape for that basin. And basically that's the hydrograph recession factor. It's the ratio of the falling limb of the hydrograph for the basin to the rising limb. In this case, we'll just use the default values of, you know, the minimum would be a 1-to-1 hydrograph, so the falling limb and rising limb are equal. The most probable value is 1.85, so the falling limb is almost twice the rising limb, and then our maximum is 4.4 times. So the falling limb is about 4 times, and that gets stochastically generated from event to event. So we've specified everything, and now we're going to accept our updates. And then that warns you that this BDF is -1, so we're using imperviousness to do the timing of the hydrograph. So there's Howard Brook. And again, I should say that here we have our little question mark. If you want to learn more about this, you know, you can look into it. And also there's always the manual and some of the supporting reports. I should say that we've done simulations, and you don't have to worry about getting the exact number for any of these variables. There's so much uncertainty in all environmental variables that, you know, you want to get the best number you can, but you know, you don't necessarily have to get the perfect number for any of these particular variables. All right, so we've demonstrated how to enter the basin properties, the project, the form. Now let's get into the hydrology form. So this is the second stretch here. So what we have here is, again, we have nothing defined here. So we want to select a precipitation data set. So we have the EPA 89 and the Federal Highway 2010. And then for right now, let's just use the average of ecoregion statistics. So I pick which one of these 1, 2, 3, 4, 5, 6, 7 sets I want to use, and I make that selection. Then I just generate and examine the statistics. And again, when you go through it, you can hit these question mark buttons to get more information. So now I'm just going to accept updates. Yes. And so you see now I have a choice. And then I can view these related sites. So this comes up. You can see it's highlighted. And all I would need to do is open an Excel spreadsheet. And if I bring it over, this is designed to be tab delimited, so it kind of looks ugly in the text format. But if you drop it into Excel, you can see that oh, here's all the rain gauges and here's the statistics each one provides. Now, I made it sound like the jump from a level 1, which is just using regional data, to a level 2 was high, but actually it's pretty easy to do. In this case, I'm going to enter a new definition. I'm going to say yes. Okay, and I have user defined, and I want to do a selected station average. So I'll pick that, and then I'm going to generate, examine the statistics. And what this does is it allows me to pick nearby rain gauges. So they are listed down below in the order of proximity to my site of interest. And a common theme in the SELDM world here will be that the things that you get to pick from are usually in a lower window, and once you pick them, they go to the upper window. So you'll kind of see the pattern. So we can see that the closest one is the Worcester Regional Airport, which has 65 storms per year and about 44.35 inches of annual precipitation, runoff generating precipitation. Whereas Bellingham is the next closest and gets 50 events per year. That's a pretty big difference, and that's a big difference in precipitation. This is where I know something about Worcester. It's kind of up on a hill, a high hill, so it kind of scrapes a lot of rain out of the clouds. So that's not really representative of my system. So I'm going to use the average of the next two. Oh, yeah, when I pick one, the statistics for that station comes up and asks me, do I want to include this station? Sorry, I was clicking through that too quickly. Well, I could say yes. So I think Worcester is not representative of this area, even though it's the closest because of that, that the effective elevation. And I'm going to take the average of these three. And once I pick the three, I can preview my average. So these will be the statistics I get. And now I create new. And it says, do you want to update these? It tells me what will happen. And so it comes up with Federal Highway 2010, which is the data set. It says average of 3 stations, and it gives the date and time today. So I will say average, I would just leave it at average of 3 stations near Northborough, and I'll say okay. And now you see I have my ecoregion values, and I have the closest, well, not the closest 3, but 3 representative stations. And now if I view related sites, that window pops up, and if I paste this in, you can see that, okay, there's the statistics for the sites that I've chosen. Okay, let's proceed. And now we did precipitation. Now it comes to stream flow. And we're just going to do the ecoregion average here, generate, examine statistics. Yes, accept updates. And again, I can enter a new definition and then pick stream gauges. I guess I could do that really quick with a lot less explanation. So I do selected station average, generate, examine. So Howard Brook was 1 square mile. I might not want to use one of these 110 square miles. Let's say if I think that I'll take the average of Quinsigamond, which is close, and Neshoba, which is a little farther away, but it's a smaller basin. And if I create new, average of 2, I just say Quinsig, and you don't necessarily need to follow me on doing these examples. You could just use the ecoregion value, or it's easy enough to click enter new, selected station average, and then go. So you could see that is easy to do, but you want a little engineering judgment on which one you pick. So then we get to our volumetric runoff coefficients. We have our highway site and our upstream basin. Based on the imperviousness values we put in, the statistics are generated using equations that we develop in the SELDM development process. They're lower than than you might see if you're familiar with the Schuler equation. He would predict 95% runoff coefficient. But when we look at actual data, we see that there's a lot of loss. There's about 20 to 30% of losses on fully paved sites. So this is based on data from, I think, 77 highway runoff stations. And then the upstream basin, the non-highway sites are based on, I want to say like 136 different study sites. And then so with the upstream basin, we also have the rank correlation with pre-storm flow. So if you're familiar with like curve numbers, this would be kind of with the same goal in mind as having antecedent wetness. So we did a lot of statistics on a whole bunch of sites nationwide, and we found out that pre-storm flow is a better indicator for antecedent wetness than other things for stream basins. Because, usually when the flow in the stream is high, it means that the basin is fairly moist ahead of time, in terms of high and compared to its normal state, I guess. So antecedent wetness tends to vary with pre-storm flow. So we have our highway site. There's our runoff coefficients. You can use the Schuler numbers, and you can use the SELDM upstream numbers. So you can choose them or you can enter your own. So we're just going to accept these updates and then click OK and proceed. Now we come to the highway runoff water quality. So what we'll just quickly do, I know we're kind of getting a little late in the day. We'll pick total phosphorus from the highway, and then we'll go to our upstream transport curve. So that's a relationship between flow and concentration. So that'll be our upstream definition. And then we'll do our downstream pairs. I know I'm going, well, so when you come here, if we pick our total phosphorus, you can see there's our highway definition, there's our upstream definition that we picked. And so we'll call this TP for total phosphorus, and we'll call it no BMP. And we won't click the BMP button. So we'll click accept updates, and then we'll enter a new one, and we'll do TP with BMP. So this is what we're doing here. I should have been more descriptive. What we're doing is we're pairing highway and upstream water quality to get what the downstream pair will be. So this is with BMP, so we're going to click this BMP button. And the concentration of concern, I should explain, I don't think anyone has used that, but this would be if there, let's say we're looking at total phosphorus, but you're worried about orthophosphorus, but you don't really have a lot of orthophosphorus data, but you might say, oh, orthophosphorus, we expect it's going to be 60% of the total phosphorus. So you can put in statistics here to get at that concentration of concern. What's my estimated concentration of orthophosphorus from total phosphorus? Or let's say dissolved copper from total copper, or with the bioligand model, you might want to be looking at like what's the the biologically toxic copper versus the total copper. So that this might be your concentration of concern. Again, I'm not sure anyone has actually used that outside of kind of an academic exercise. And then for your pair, you have this description, so you can tell what you're pairing and why you're pairing it. So now we accept updates, proceed. So on the water quality form, we now have total phosphorus, no BMP, and total phosphorus with BMP. If we're simulating a number of different total phosphoruses, then we probably want to get a little more descriptive on these. You can have up to 50 characters. So once I can select them, I can just click them and it will say, you have selected this, do you want to keep it? And I say, click yes. You've selected this, do you want to keep it? I click yes. You can, there's some of these features over here on all the menus. You can view this. So if I view it, it pops up the definition. And again, we have our little question mark button. It tells me what I'm doing with it, what a water quality pair is. And so I have defined a highway runoff water quality. I've defined upstream runoff quality, and I've defined downstream water quality with a BMP and without a BMP. So now I'm ready to proceed. Now, the default is no BMP in place. And even though I said BMP and no BMP, if I don't specify a BMP, those numbers should be identical. What we did was we did for Federal Highway a data mining exercise where we took the 2019, the latest version of the International BMP database that was released, and we ran all these BMP statistics for all the BMPs that had enough data. So we came up with statistics for all these different types of BMPs. So what we see is we talked about, we called this analysis grass swale 2020. And you can see that if we edit this, you can, this description has all kinds of information in it. Let's see, I can copy that. And if I paste that into Word, you can see this gives, where the reference for all the information, and these are all the parameter codes for the different water quality. So there's the hydraulics for a grassy swale. Here's all the water quality parameters we were able to get definitions for, and this is the water quality treatment statistics for the individual BMP, for suspended sediment for that BMP. So I'm going to just select the current, that grass swale, and then we'll proceed. Now here, if I click information and see this analysis status, you can see we've gone through and we specified all the hydraulic and water quality variables, so now they're checked off. So if I close the form, the information form, now I can proceed. And then you come here, you have some output options. You have percentiles, units, sorting order, how many significant figures. most environmental variables are reported to 3 significant digits, so that's our default output. If you want to check calculations and try and get the right, figure out if all the inputs will result in the outputs, which we've done many times, you could do this double precision. But don't think because you have 15 digits of precision that your answer is precise, I guess. And so we just run SELDM. And we see that so you can see that took about a minute, maybe less than a minute. So then what we can do is we've gone all the way through, we've defined everything. We can either exit SELDM, as if you had noticed, like if you have to go to the bus stop and pick up the kids, exit SELDM is on every form, so you can exit and it will just save everything you've done and get out. Right now, since we ran that analysis, well, one thing we'll do is if we come here, we can open our output file. So we can see we have a documentation file, precipitation file, highway runoff quality, upstream runoff quality, dilution factor file, pre-storm flow, storm flow, highway runoff file name, and downstream. So you have all these different outputs. And if you click that button, it opens the output file. And when we worked with EPA, they were worried about people going in and monkeying around to get the numbers they want. I guess maybe the person we were working with is a little more, maybe they've seen a lot of things. But so SELDM puts it in a predefined directory, basically on your root drive, FHWA-SELDM, it makes a folder, and then the project name is the next level folder, and then the analysis name is the next level folder, and then it's the date on which you made the run and the run number. So this was kind of like verification. So if you open this up, you can see the date and time stamp there is the same as, the file timestamp. And you can see, and that's again, just for, EPA was concerned that people might be changing their answers if they didn't like them, or I don't know. So let's go back to the analysis form and then I'll let you go very quickly thereafter. So you can see we can go to the precipitation form or the BMP form. So if we go back here and we have our analysis, so we just copy this analysis, yes. And let's go, we'll call this one, I guess, wet pond. Wet pond, maybe 2 words. Okay. Then I copied the analysis. So we can see now, because we copied it, we have all that information. So we can close that. And now we just have to click all the way through this because we already specified everything. So we said this one's going to be wet pond. We're already at the BMP and I guess not wetland basin, but I guess I should have called it detention basin, right? Detentions are wet. And I can go back and change the name of that, but we won't right now. So we chose the detention basins. So now we're getting all the hydraulics and water quality treatment for our detention basin. So let's proceed. And again, I run SELDM and it runs. If you try and do a ton of runs, it can slow down over time based on what's called database bloat. So sometimes it's good to get out of SELDM, then come back in. And so if we see the We can see the file names. This one was Howard Brook Swale. This one's Howard Brook Wet Pond. And we have all the same outputs, but you know, the effect of the BMP will change the answers somewhat. So if we come to fall class, you can see we have those two under this. The project is fall class, and then the analyses are Howard Brook Swale and Howard Brook Wet Pond. And if we ran this again, we'd have run 1, run 2, run 3, run 4. All right, I think so. We've gone through an example. We kind of did the introduction. I guess I will stop recording, and we can, if anyone has any questions, we can, you know, discuss anything or go back to any particular form you want to look at and ask a question.